For 8b.3, we are going to be learning some of the rules of logarithms and applying them to different problems, and then we're also going to be graphing logs onto a graph so you can see what they look like. So to start, we are going to learn 3 special rules of logarithms. There are a few more rules of logs or properties of logs that we're going to be working with later, but today we're just looking at the special rules. So here they are. First rule, if we have a base b and that base is being raised to the power of a log, so you have a number and then in the exponent is a log, the base of your the base and the log will in the exponent will cancel out, and your answer will be the number that you are taking the log of. The second rule, if you have a log base b and you are taking the log of an exponent and the bases are the same, so b and b will both be the same number, those are going to cancel out, and your answer is going to be the exponent that you are raising the log to. And then the last rule that we're going to look at today, if you have log of any base that you are taking of 1, the answer will always be 0 no matter what, because your answer comes out to 1, and anything to the 0 power gives you 1. Just as a note, b and y will be positive numbers. Your base can never equal 1, just as a reminder, and we're going to look at a few problems like this. So, example 1. I have 6 to the power of log base 6 of 27. So I have a base, and I'm raising it to the power of a log, and the base of that log is the same. So we're taking an exponent of a log. So those are going to cancel out, and my answer is going to come out to 27. Number 2, I'm taking log base 3 of 3 to the 5th. Now we did a problem like this the other day where it was a log base 10, and we set the whole thing equal to x, we brought it all the way around, and it ended up already having the same bases. So if we were to look at this problem and we said 3 to the x equals 3 to the 5th, I already have the same bases, so x equals 5. Now that we know the shortcut, I notice that my bases are the same, so they just cancel each other out, and my answer is the exponent, which is 5. Example 3, I am taking a base of 10 and I'm raising it to the power of log of 2. Now the log in my exponent does not have a base written, so we can assume that the base is 10. So the base of my the base of my number and the base of my log are exactly the same, so it all cancels itself out, and my answer comes out to whatever we're taking the log of, which was 2. So I'm giving you the rules and the shortcuts, and I want you to apply them to specific problems. That's all we're really doing here. So number 4 is log base 6 of 36. Now we could go through the entire process, but I notice that 36 is the same as saying log base 6 of 6 squared. So now my bases are both the same, so they cancel out, and my answer comes out to the exponent, which is 2. Number 5 is very similar to number 4. It is log base 5 of 125 to the power of x. This is the same as saying log base 5. 125 is 5 to the 3rd, so of 5 to the 3x. So now my bases are the same, so they cancel out, and my answer is just the exponent, which in this case is 3x. Number 6, log base 4 of 1. I just gave you that rule. If we're taking log of 1, no matter what the base is, your answer always will come out to 0. And the reason being is because the only exponent that will give you an answer of 1 is 0. So it doesn't matter what your base is. If you're taking a log of 1, your answer has to be 0 because that is your exponent. That gives you an answer of 1. So, just as a reminder, if there is no base shown, you can assume that it is a base 10. That is called the common log. So if we have log of y equals x, that's the same as saying log base 10 of y equals x, so you can add it in there if you want, which is the same as saying when you come up and around, 10 to the power of x equals y. That's just a little reminder. So remember, you start at your base, you go up and around. So that's 10 to the power of x equals y. So let's look at a couple problems that deal with a log base 10. These are actually examples 7 and 8. So example 7, log of 10. This is the same as saying log base 10 of 10, and there is no exponent here, so it's 10 to the first. So that is the second rule of logs that we looked at, because my two bases are the same, so they cancel each other out, and my answer is just the exponent, which is 1. Number 8 is log of 1 over 1,000. If we're trying to apply our logs, our special log rules, we need to get this 1,000 to have a base of 10. So that's the same as saying log base 10, and to move this up is going to be 10 to the negative third power. I can cancel out my logs, and my answer comes out to negative 3. Which is the exponent. We're going to learn about a new number in math. So we have a new number in math called e, and we write it as e. E is given its name because it was discovered by a German mathematician named Euler, who spells his name E-U-L-E-R, and he discovered this number, so they named it after him and called it e. It's an irrational number like pi. So how we know pi is approximately 3.14, we can estimate e to be approximately 2.718. And it goes on for longer than that, but forever, just like pi does, but we estimate it to 2.718. And there are special logs that use e as its base. So if a base of e is used, it is called a natural log. Okay, so it's a special type of log called a natural log, and it's just a log base e. But instead of writing log base e, we have a special notation that we use called ln. So ln stands for log natural. We read it natural log. So if we have ln of y equals x, that's the same as saying log, and the arrow moved over a little bit, log base e of y equals x. So when we come up and around, it would be e to the power of x equals y. So it's a similar idea to a log base 10 where you don't have to write the base. So if you ever see something written as ln, you could rewrite it as log base e. Okay, so the 2.718 is your base in that case, and we have a special notation for it. Okay, so just as a reminder, E is just an irrational number. It's approximately 2.718, so it's not a variable. E actually stands for a number, just like pi actually stands for a number. So you'll never be able to solve for E because it's just a letter that is used to represent an actual number. So numbers 9 and 10, we're going to practice with this a little bit. And I just want you to rewrite the numbers in exponential form. So number 9 is a log base pi of 31.01 equals 3. So we go up and around. So that's pi to the power of 3 equals 31.01. And that's all they want us to do is rewrite it in exponential notation. So let's do the same thing for the natural log. Natural log, remember, is the same as saying log base E of 20.01 equals 3. So when I come up and around, that gives me e to the power of 3 equals 20.01. Eventually you will get to where you do not have to write this step, but just since we're practicing so that you can actually see it, I rewrote it. But if you ever see it written ln for the natural log, you do not have to rewrite it as a log base E. So let's graph a little bit and then we will be done for the day. So to graph a log equation is actually very similar to graphing exponential equations, which we did in Unit 8A. So to graph a log equation, you're going to first rewrite the whole thing so that it's in exponential form. So it's going to actually look very similar to what we're used to. And then you're going to make a t-chart or a table of values. But the important part here is to look at the equation and see which letter, x or y, is in the exponent. So whatever variable, x or y, depending on how our log is written, is in the exponent, that is where we are going to put the numbers 2, 1, 0, negative 1, negative 2. So you plug numbers into the exponent, not into the answer, because it's easier for us to plug numbers in than it is to figure out what a specific number will spit out. So then you're going to plot those points and connect them. So example 11, we're going to graph y equals log base 3 of x. So the first thing we're going to do is rewrite this in exponential form. Now, this problem has y on the left-hand side. Usually we're used to it being on the right with logs, but it's the same idea. So we have a base of 3 to the power of y, and it equals x. So because y is in my exponent, we're going to plug in 2, 1, 0, negative 1, negative 2 into the y column, because it's easier for us to plug numbers into the exponent than it is to plug numbers in here and try and figure out what exponent gives us that answer. So if I were to plug in 2 to the exponent, that's 3 to the second, which is 9. If I were to plug in 1, that's 3 to the first, which comes out to 3. 0 always gives me 1, so that would be 3 to the 0. 3 to the negative 1 gives me 1/3, and 3 to the negative 2 gives me 1/9. So to graph this, you're still going to graph this x comma y. So our first point is going to be 9 comma 2. So we're going to go right 1, 2, 3, 4, 5, 6, 7, 8, 9, and up to Didn't mean to put a point there. Our second point is 3, 1, so we're going to go right 1, 2, 3, and then up 1. Our next point is 1, 0, so it's going to be right here. Okay, now the next point is going to be tricky. 1/3, -1. 1/3 is between 0 and 1, so it's going to be about here. And then -1, we're going to go down 1 whole space. And then 1/9 is even closer to the y-axis, but it's still between 0 and 1, and we're going to go down -2 spaces. So our log function, it actually looks like this. So it's almost identical to those exponential functions that we graphed in Unit 8A, except that it is rotated 90 degrees. So instead of getting very, very, very close to the x-axis and never crossing it, we do cross the x-axis, but we get very, very, very close to the y and never actually touch it. So it's a log function is like an exponential except rotated 90 degrees. So number 12, we're going to graph an exponential function and a log function on the same grid so that we can see the difference between the two. So I'm going to do my exponential first. So my exponential is y equals 2 to the x. Because x is in my exponent, that's where I plug in the numbers. So 2, 1, 0, -1, -2. If I were to plug in 2, that gives me a y of 4. If I plug in x equals 1, that's a 2. 0 always gives me 1. -1 is going to give me 1/2, and -2 is going to give me 1/4. So let's graph that first. So my first point is going to be 2, 4. So we're going to go right 2, up 1, 2, 3, 4. And then the next point is 1, 2. So that's right 1, up 2. 0, 1. -1, 1/2. So left 1 and 1/2 is right in between 0 and 1. And -2, 1/4. So that's left 2 and 1/4 is between 1/2 and 0. So this is our exponential, exactly what we graphed in Unit 8A. It gets very, very close to the x-axis but doesn't actually touch. And then let's label that y equals 2 to the x. So let's graph the log function. If I were to rewrite this as an exponential, it would be 2 to the power of y equals x. So it's almost the same except x and y are flip-flopped. So because y is in the exponent, I plug in 2, 1, 0, -1, -2 for y. So if I were to plug in 2 for y, that would give me x equals 4. If I were to plug in 1 for y, that gives me x equals 2. 0 gives me x equals 1. 2 to the -1 is 1/2. And if I were to plug in -2, that gives me 1/4. So to graph this one, my first point is 4, 2. So I'm going to go right 1, 2, 3, 4, up 1, 2. The next point is 2, 1, so right 2, up 1. The next point is 1, 0, so right 1, and then I stay on the axis. 1/2, -1, so 1/2 is between 0 and 1, and then I'm going to go down 1 space. And 1/4, -2 is between 0 and 1/2, and then I'm going to go down 2. So my graph of my log gets very close to the y-axis, but doesn't actually touch, and that's y equals log base 2 of x. So my two functions are actually symmetrical about the line y equals x. So if we were to draw a diagonal line right through the origin, and were to fold on that dotted line, these two graphs would be symmetrical around that line. So we would say that exponential and the log graphs are inverses of each other, which is what we did in Unit 7. So a log function gets very, very, very close to the y-axis but doesn't actually touch it, and an exponential function gets very close to the x-axis but doesn't actually touch it. So that's the difference between graphing exponential functions and log functions, although the process is still exactly the same. But the graph of logs should cross the x-axis but not the y.